now is actually the interesting side for us. I mean, mostly because the side which shows that if you have bounded coloring numbers, you will have bounded expansion. So that means that, well, you can just work with coloring numbers and you will imply things for bounded expansion. But the reverse is also true. You can also say, I'm interested in a bounded expansion class. Well, then you can, like Zuding Zhu is telling you that you can find a nice ordering. So, we start?
Yes.
Okay. All right. So let's officially start. Okay. So just maybe to recall these ideas. By the way, are there any doubts that needs to be clarified? I'll briefly recall the flavor of the definitions. So we have these two types of coloring numbers, which are, generalization both of the degeneracy. You take an ordering, sigma, of your vertices. So just to clarify, because I had some questions, I mean, this ordering is completely arbitrary. I can define these notions for any ordering. You may have edges between consecutive vertices, you may have no edges, we don't know. We don't know anything about how the edges are structured of this graph. We're just giving some order. So if there are n vertices, there are n factorial possible orderings. I'm just taking one sigma. Okay. Of course, then I will optimize over all possible orderings. But these notions I can define, these notions of weakly reachable and strongly reachable, I will define for a particular ordering sigma. Okay? So what did it mean? Weakly d-reachable from a vertex vj here. It is all the vertices which are smaller. I'm only looking at the small ones, which you can reach from vj to vi in at most d steps. So there is a path of length that is d. And weakly reachable means that I can only use vertices which are to the right of vi. So I cannot go on that side. So this path has to be completely here in this ordering. This is a weakly reachable. So we can define the set of weakly reachable vertices here, given a particular graph, a particular ordering, and a particular starting vertex, vj. All the ones which are weakly d-reachable, of course. Oh wait, d also. D is important. I usually forget to write in d. There also. Okay, and strongly reachable is more restrictive, as the name suggests, because now you also cannot use the vertices which are sandwiched between vi and vj. You can also not use the ones which are smaller than vj. So here your path is more restricted. It has to, start on the right of vj and do whatever it likes. And the last edge goes to vi. So this is the stronger definition. So this, of course, the set of strongly reachable vertices, d-reachable vertices from vj is smaller than the one of weakly reachable, because strong d path like this is also a weak d path. Okay, and then these coloring numbers, weak coloring number and strong coloring numbers, are just the minimum over all. You want to minimize the maximum size of such a reachability set. So for a particular ordering, you take the maximum size of a reachability set, and you take over all possible orderings, the minimum of this. So it's a min-max parameter. Okay. Exactly like the degeneracy was the minimum of all possible orderings of the maximum number of left neighbors of the given vertex. All right. And so this morning what we saw, essentially we saw that these two notions are kind of bounded by each other, some functions of each other. So when we say one is bounded, I mean, it means the other one is also bounded, and vice versa. Let me make one important remark, which I didn't do in this morning. When you look at when you look at these coloring numbers, let's say weak coloring, strong coloring, but also for different d's, the ones which are optimal could be completely orderings. It could be that for d equals 1 you need one order, then d equals 2 you need another order, d equals 3 you need a different order. So there is nothing which tells us that this ordering sigma has to be the same for all these parameters. of bounded expansion. And for these classes, right, because these notions can be defined for any graph class, any graph. But actually, I will just make a small remark that there is a so-called universal orderings which exists. So this will be just a side remark. This is called universal orderings. If you're interested in that, it can sometimes be useful. This was proved by 2018 by Van den Heuvel and Courcelle. But this works only for graph classes of bounded expansion, so see a graph class of bounded expansion. Then you have a function f, which will basically bound all these numbers. For one, so all these numbers for one given sigma. Such that for every graph in your class, bounded expansion, there is a sigma for this particular graph, which will work for everything. Take the same sigma and this weak reachability numbers will be bounded for it. And okay, what about the strong? I mean, the strong will follow, because what we proved this morning essentially is that, you know, given particular ordering for the weak, it will also work for the strong. If I remember it should work. So that same sigma works and bounds everything. It is quite nice. For all the values of g of the same ordering. Maybe the function, you know, becomes bigger, but anyway, these functions are arbitrary, so there we go. You might as well compromise on the function and get the same ordering.
This sigma depends on g, right? Not on c.
The sigma depends on g. Of course, because I mean, sigma is an ordering of this vertex of this graph. Because it's universal for all d. Universal for d. So let's say d universal. Because it could have been that for d equals 1 it's one ordering, for d equals 2 it's another ordering, for d equals 3 another ordering, and so on. No, you can find one ordering for all d. This is the point of this theorem. If I'm doing the remarks, maybe another last remark. It is so. I told you that many things work similarly for no-dense graphs. Just a very small remark, but for no-dense graphs, what you will get, you will. These functions will, so these, you will also get orderings for no-dense graphs, but they will not be constant. So these coloring numbers will be basically, so just a note, for no-dense. Classes, F, so these coloring numbers, C will be at most. There will be some epsilon. This will be a fixed function. So you will have something like that. So these coloring numbers will no longer be constant. They will depend on the number of vertices. This is the number of vertices. But this is a small epsilon, any epsilon you want. Imagine like 0, 0, 0.1. It will not be constant, but it will be relatively small. If you take epsilon n 1/2, you will get square root n, right? So imagine something like square root n, smaller. Sorry? The ordering is universal. Universal for D.
So sigma is D universal ordering.
Yeah. It means that it will bound the coloring number. Like the coloring number will be bounded for the same sigma for every for one graph. So for each graph, there will be an ordering such that this thing is bounded for all values of D for the same sigma. You can just choose the same sigma.
Is there a simple example of such a graph class?
Of what?
Of such a graph class?
Of no dense graph?
Which admits a universal ordering?
Well, all the bounded expansion classes. See a graph class of bounded expansion.
Oh, all of them admit?
All of them have a universal ordering.
Oh, I see.
This is what they proved.
Oh, I see. Oh.
Yeah, it's a strengthening. It's a strengthening of this because this just says that, well, for every graph and for every D, you have an ordering. Here it says actually you can just take for every graph one ordering. Which is quite nice. And simplify things.
So what is that dependency on the variables for the function?
Which one? Here?
In the note, f of
C epsilon. C is the class. F of.
what do you mean?
Well, okay.
So already that here that A is depending on the class.
Oh no, it's a D. Sorry, it's not the C. I mean, F is the pure. F depends on the class anyway, so it's a D. It's D. So that function is a function from the class. Yes. So thanks for the correction. So the function depends on the class, and then for every epsilon, you have some function of D epsilon. It's not very important. It's just a side remark. And by the way, if we are still making a side remark on no-dense graphs, I think I said it this morning maybe, I don't remember. But these guys, this is not related to this, but these no-dense classes, they will have O of n to the 1 plus epsilon edges. So for bounded expansion, you really have to think that there are linear number of edges because the degeneracy is bounded. But it's not true for these no-dense graph classes. But it is very close to linear. So there is some epsilon such that this number of edges will be. So, okay, maybe one thing I want to tell also, maybe one intuition, I mean, why also I like these bounded expansion classes. You know, I mean, also when I prepare the lecture, these proofs are they are readable, you know? Like when you take these H minor field graphs, you have these 20 papers by Robertson and Seymour that you need 20 years to write and 40 years to understand. So, and you can only write them if you're Robertson or Seymour, or both combined, actually. So it is very difficult. It's very technical, and whatever you read the papers, it takes a lot of time to understand. Of course, once you have invested your time, you understand. Maybe you can simplify this, and then you can work with it. But I find that the proofs here are quite readable. You know, I mean, some of these nice proofs are like 1-2 pages long. It's not that difficult. And, well, of course, I mean, I took great inspiration from this lecture series by the Philippe brothers. They also, makes you digest the material nicely and inspires to make these kind of lectures. But yeah, I think this is a nice theory, and you can manipulate these concepts not in a too difficult way, and understand what's going on. Okay. So let's try to prove that 3 implies 1 in the theorem of Joux, which means that if I can find if the weak coloring number is bounded, then my graph class will have bounded expansion. Okay. In fact, what I want to show this, what we will say, is the following. Here. So what I will actually show is that we take G. And what I will do, I will say that the edge density of a shallow minor at depth D, of a D shallow minor, of G, I want to prove that this is at most the weak coloring number, but with this D a little bit augmented, 2D plus 1. Okay. See that here we are doing this for every D, so it doesn't really matter whether I take D or 2D plus 1. This thing will be bounded anyway by a function of D. This is D. So whether I take D or 2D plus 1, anyway it will be bounded. Right? So what I will do is basically I will take D shallow minor of my graph. And using the ordering, I will remember the order, and I will show that this D shallow minor doesn't have too many edges. I mean, edge density. Okay. So let me see. So let's sigma be one ordering which works well for this. So we take an ordering of the vertices of G. And I want that the weak coloring number at distance 2D plus 1 G sigma is at most well some function, which I denote by K. So I say it is some number K. Okay. Actually, practically, you put this F2 there. F2 of T plus 1 is some number. And I look at the shallow minor. So this is my minor model. Okay. So this will be E1. J, etc. So what it means is that I have a central vertex of this, and this is a subgraph of radius at most D. Okay, let's call these central centers Ci, C1, Ci, Cj for center. And then, well, let's say that H is this graph, so of course I need some edges here. Lots of edges. That's how the situation looks like. But then, obviously, I could have also more things. So I may have things which I don't really care about, but they exist still. There could be picture and remove these things which we don't need. Okay. So remember that in the minor relation you're allowed to delete things. So I'll just delete whatever I don't need. So just to make a picture clearer, I'll delete these yellow things. So what happens after I do this, I basically just get some kind of spanning tree here of my branch sets with the center as the center of the tree. And here are the connections. So there are other things here. I'm just not drawing everything. And actually, you know what? Let's just keep one edge between every two branch sets. We don't need several. Let's just keep one. And now let's look at the subgraph between two of these branch sets. We focus on these two. Let's call this V. Actually, let's rename them Vi and J. J here. And in this subgraph, now that I have kind of deleted things which I don't care anymore, this is actually like a tree. You have the spanning tree, and one edge which joins them. This is in fact a tree. And let's look at since it is a tree, there is a unique path from Ci to Cj. Looks like this. So this is an edge, huh? This is not a path, this is an edge.
So now you are considering only the spanning tree of this particular path.
Yeah, I mean, this is not a tree, there could be a cycle, right? So it's this. But I'm focusing on this part. If I focus on just these two branch sets, it's a tree. I think it's a tree. Because I kept only one edge. I just kept the bare minimum that I needed to get my h as a minor, as a depth D minor, right? The rest I didn't, just to simplify the picture. I don't think it's that important, but it clarifies things because now what is important to me is this path, and now I know it's unique, so it's well defined. So I will look at this path. Okay, what's the length of this path? So remember that 2D plus 1, yes, correct? Most 2D plus 1 because this is at most D, so at most D, and this is 1 edge. So L of P at most 2D plus 1. This is actually why I have chosen 2D plus 1. L of P is at most 2D plus 1. Okay, and let's do the following. Let's consider minimum. I will say MIG. I'll write in white. MIG is the minimum. So remember, we had this ordering, right? I'm now going to use it. I've not used it yet. I've just looked at my minor model. Using this ordering, and I say MIG is the minimum vertex of P, minimum with respect to sigma. So I take the smallest, it's a single vertex, it's the smallest with respect to the ordering on this path. I mean, the ordering, we don't know what the ordering looks like. Right? But this path could be anything. Now I have no. This path is just an arbitrary path which I got from there. I don't know anything about these reachability rules or whatever. It's just a path. Okay. Okay. Let's suppose it's like that, and this is Ci. This is Cj. I only know it is at most 2D plus 1 the length, and this will be MIG.
Vi and Vj are the centers inside those branches.
No, Ci and Cj are the centers. Vi are the branch sets. I call them Vi for vertices. So Vi is capital V.
Okay. The path P is between the centers Ci and Cj.
Yeah, center C and Cj, so it's kind of the unique path when you strip your graph of just these two
Okay.
things, there could be other paths like this, and like this. I want this because it has length 2D plus 1. So I'm taking this. Alright. Control what's happening here. Yes, correct. Okay, now let's look at where is this MIG. There are only two options. It could be close to could be inside VI or inside VJ. Okay. Alright, let's say it is here. Okay. So now this is here. So if I do this, I will basically do an orientation. So
What is R over there with respect to R?
Sigma.
Oh, sigma.
sigma, yeah. That's why my R's and my sigmas are very close, so that's why I'm using D and not R. There is no R. If you see R, it's a sigma. Yes. So it's not universal, it's universal sigma set. Okay. So I'm orienting, and of course this gives me an orientation of my H. What am I trying to do here? I mean, maybe you see it coming. I'm trying to give an orientation which will prove that the degeneracy of H will be small. Remember, there was Shaglin yesterday gave an equivalent definition of degeneracy, and that was that you can find an orientation which is acyclic and what was it? There is always a vertex of integrity at most D.
All vertices need integrity.
Sorry?
I think all vertices need integrity at most k.
No. One.
Well,
Okay, how are we going to do this? Okay, I mean, now this is not difficult. I have to count the number of incoming neighbors. Okay, out degree. Okay, let's already do it. It's the same.
Doesn't matter.
It really doesn't matter because you can just switch, but let's stick to the same thing. So, actually, this is even better because I'm pointing towards MIG. It's kind of better. So I'm going trying to plot the out degree. Yeah, in fact, you know what? I will in fact bound, I think, the out degree of. Yeah, I will bound the out degree of everybody. Yeah, I think you're right. It was for every vertex, right? Every vertex, the out degree. Yes, because you're kind of orienting. You take the ordering and you orient everything in the same way. So yes, I will bound the out degree of everybody. Okay, how do I do that? Well, the main claim you have to see is that let's look at the CJ and look at this MIG. I want to count what is the number of out edges. It is the number of MIGs that can be located on the other side. But the point is that if you look at the path from CJ to MIG, it has length at most 2D plus 1. And this guy is minimum on this path. So I take a subpath of P. So this is clearly a path. And I know that this is minimum on the red path, so it's also minimum on the blue path, no? So now I'm looking at this blue path. So if you look at here, so now I don't care no longer about CI. I look at MIG and I look at CJ. So the blue path looks, well, here it is very easy. It's my
What do
example.
you mean by minimum being such that it belongs to the path?
It is minimum for the sigma, the smallest.
Okay.
This picture.
Okay.
You have the red path, and MIG is the smallest in the path. It's well defined because, I mean, we have no idea how this path is. But now I'm interested in the blue path. Okay, so that blue path, let's call it P prime. Okay, so we have length of P prime at most P plus 1 because, it's at most, in fact, it's at most the length of P, which is at most P plus 1. It could be exactly equal to D plus 1 because it could be, that MIJ could be equal to path is the path which goes from Cj to Mij, and which is a subpath of P. P goes from Cj to Ci. So I'm just stopping when I reach Mij. Then Mij is somewhere on that path. So that length is at most 2d plus 1. This is minimum in the path. So now I can use my weak reachability. That means Mij, I conclude that Mij belongs to W reach G sigma Cj. And 2d plus 1. 2d plus 1 because the path is the strength at most. Right? This is by definition of weak reachability. Because, well, I'm using only things which are bigger, but I might use something which is in between Cj. It's weak and strong. But now we have the proof. Because, why? Because we know this is bounded, right? This set is bounded. So the set of all Mij's, so for fixed I, the set of Mij's which will be in this situation is at most the size of this weak reachability. And this is bounded, so we are done. So if you look at, so what's the L degree? Let's say d plus of Vj in H is at most the size of the Mij's such that what did we do? Right? Sorry, it's the number of Mij's such that Vj is an edge in H, and Mij belongs to big V I. Does this make sense? So the out degree of Vj in H, so Vj I'm making correspond to capital Vj here. It's just the maximum number of Mij's. So so this J is the same J here. Vi Vj is in of H, and we can say Vi is in H. This was Vi chain in N. And this Mij is capital Vi. And now I just proved that Mij is in the set of these Mij's is included in the weak reachability of my Cj. So this is at most the size of weak reachability G sigma Cj, 2 plus 1, which is this degree. It's this constant thing. We know the weak coloring number is constant.
So please explain how you get the degree at most that set. Degree of Vj.
Because for each out edge, I need this some Mij in this, right? So if I have another out edge, let's say this, I do the process for every edge, right? I didn't explain that. I do this for every edge, and now. If this was the I prime, I have some mi prime j. Okay, maybe mi prime j is here, and then I run it like this. That is fine. I don't care. I just want to bound the out degree. So, in case it was here, I do this. So I want to count the number of out edges. But I'm saying, each time this happens, this Mij is in the weak reachability set of this guy.
Yes.
So here I have 1, I have 2. So but this weak reachability set is not that big. I have at most k spots. I'm already filling 2. At the worst case, you will have MIJ, okay, these MIJs are distinct obviously because the balls are, these branchets are disjoint. So these MIJs are all distinct. So the total number of MIJs is at most the number of weak reachable vertices, which is at most k.
But then we are only able to bound one VJ. VJ of one order.
No, I took any VJ. This is true for every VJ. You redo the same for every VJ. So in fact now, yes, I was wrong before. It is, we are really bounding for every VJ the out degree.
So the orientation will not change for other VJs?
No, because see, between one VI and VJ, I only considered VI VJ, I didn't consider, the order of VI and VJ was only one. So for two VI, for a pair VI VJ, I could have done VJ VI, it was the same because I considered this path, this red path, there is no orientation here. The orientation comes from the position of this MIJ. I don't know in advance, it could be either here or here.
And you are anyway overbound.
I'm only pointing towards this MIJ. This MIJ has one location either here or there. I'm pointing towards it. This is completely well defined. I can do it again and again, I will get the same outcome. Orientation is unique, well defined. It's not a choice. And now I know the out degree of each vertex is at most k. So what does it mean? Well now, that means H is k degenerate. This implies take a vertex of out degree k, you peel it off like that. So the number of edges, so there is at most k and edges, so this at most k. And this is exactly d. Well, not exactly, but this is at most the maximum.
Is equal to maximum, right?
Equal to maximum. Okay, I take the h which was, it's true for any h, right? You might as well take the h which maximizes this density. I mean, this is not really.
It's not less than or equal to, that's just.
Yeah. This is true for every h. So in particular, you take that h which maximizes this thing, and so this is nice. You know, when for the graphs of bounded degree to show they had bounded expansion, I was bounding the max degree of this h this morning. Here we are doing a bit more. We are bounding the degeneracy. Works as well. It's a bit stronger. But the idea is a bit similar. You know? Look at your h and find some. But this MIJ idea is. Are there any questions about this?
So now you prove that 3 implies 1 and 1 implies 3, it is out of.
It's an exercise. 1 implies 3 is a bit more difficult. So I will do it now. It will take an entire lecture. But actually, I think the Philip Trope products, they have a proof of it in there. If you want to have a look. There is a video and the lecture notes are quite good. So I think they do it very well. I just showed the easy stuff. And I think, the thing is, probably they will use the topological grads, which I don't really want to bother too much about. They might be using a little bit more definitions. So, good. If there there are no other questions, I will now move to the next topic. So there will be quite a lot of definitions. There will be a lot of concepts and some relations between these concepts. So it will be some application of this, but the applications might come a bit late, maybe tomorrow, I don't know. I will have time today to explain, but at least I will try to define the different concepts. I think they're nice to think about anyway, independently. And we will, basically what we will get another characterization of bounded expansion classes. So the characterization will be proved using the covering numbers, but it's a different and this topic is called the neighborhood complexity. This neighborhood complexity, I think it's a nice topic that is independently interesting for anybody who likes graphs. And it's essentially a measure of how complex can be neighborhoods. I mean, this is kind of the name which tells it. But it is with respect to a given set. So we are going to look at one set of vertices. You have a graph G. You have a set X. We're going to see how the neighborhoods of other vertices, I mean vertices could also be inside, but how they intersect X. So in the worst case, it could be that they intersect that. So this is X. You know, there could be 2 to the power size of X possible neighborhoods. I mean, intersections with this set X. But you can imagine that if this happens, your graph will be pretty dense. Right? So this is not going to happen in sparse graphs. Imagine trees. Obviously, for a tree, you would not have even this, right? You would not even have this, so if this is your set X, this would immediately create a cycle, so this kind of behavior would not be possible. Okay, so, but generally, the point of this lecture, and I think we'll continue tomorrow, will be to show that for sparse graphs, and in particular graph classes of bounded expansion, they have this neighborhood complexity, which I didn't define yet, but this idea is that this cannot happen, and this will be essentially, in fact, linear in X. So the number of neighborhoods will be linear in X. Not only this will be true for every D. If you take D, we look at the D neighborhood, so distance D neighborhood, this will still be true on graph classes of bounded expansion. Not only this, what will also be true is that when you look at the vector of distances, right, this could be distance 2, 3, 5, 10, etc., even that will be bounded on graph classes of bounded expansion for every D. Bounded linearly precisely. We will try to see that. But let's first start with a simple neighborhood complexity. So distance 1 and what's the definition of this? So it's so the neighborhood complexity of the graph G is a function. So okay, no, let's first define for a set, to be more precise, of G with respect to X, a subset of G. This is now a number, it's not a function. Neighborhood complexity G of X. This is the size of all the possible intersections of neighborhoods of G. So we take all the vertices of G. We look at how the neighborhood intersects with X. This gives you a set. So it could be that several vertices
inside X is also bounded.
Yes, we could take the inside X. But, you know, we won't care too much because this thing will depend on the size of X anyway. It will be like linear in X, let's say. And then the guys in X, they account for at most X, size of X. So it will not be very important. So also, one remark I've seen in some authors, they use closed neighborhoods. I use open neighborhoods, but at least for of course, for your specific application, it could be important, but for today, it will not be.
Differently, we also believe this can be like we have so many numbers, like v1 of b intersections. We are different partitions of the set.
Let me give an example. Let's say this is my set X. Okay? And let's say this. What is my neighborhood complexity? Let's give names v1, v2, v3. So these vertices. What are the different neighborhoods? So this one is only v3. This is 1. This guy sees v1, v2. This one sees v1, v2. And this one sees also v1, v2. So these two will not count double, will count as 1. Okay? But here this is v2, v3, and I will also look at the ones inside. So this is only itself. Let's put some edges, otherwise it will be boring. Let's say this guy sees v1, v2. This guy sees also v1, v2. And this guy sees just v3. So what is this set?
Because you're
And this one?
considering the closed neighborhood,
Open.
should this be only V2 or
This is open neighborhood.
Yeah, so if it's open, so why are we considering
Oh,
V3
oh.
or V1?
Yes, correct. Thank you. Sorry. So this is just v2 and this is just v1. Is there any other mistake?
V3 is not the.
V3 is empty. And all these are empty. So what do we have? We have empty, we have v1, we have v2, we have v1, v2, v2, v3, and v1, v3. I think that's it. 1, 2, 3, 4, 5, 6. So the neighborhood complexity in G of X is 6. It could have been 8, but unfortunately it's only 6. Okay? So that's the neighborhood complexity of a given set. And now I want to define neighborhood complexity of a graph. Neighborhood complexity of graph G and C of G. What is it? This time it's a function because no, sorry. I want to already think. Okay, let's stick to this one. This function I will do for some number k. So this will be the maximum for all the subset x. Maximum of x included in V of g, but belong to V of g choose k of the neighborhood complexity. So I'm taking the maximum of all possible sets of the same size. Observation which I already gave say it's at least one because in the worst case the empty set always either you k is 0 and then you have empty set, or k is 1, 0 and you have something. It doesn't matter. So, as I said, this is bounded for any graph classes. We will see it's bounded for graph classes of bounded expansion. So this is very well related to a notion which is called locating dominating sets, or identifying those. I might define it a bit later. Which is a kind of dominated set where you want, in some sense, to take a set X such that everybody has a distinct intersection inside X. So here we are fixing the size of X, but now you could imagine a problem where you are not fixing the size of X. You are trying to grow your X until everybody has a different neighborhood inside X. In the sense that basically the neighborhood complexity of X would be exactly the number of vertices. Come back to that. Maybe I want to prove some things. Depending on the time, I don't have to do the time. 1 hour. Let's do a couple of things. Because we have time. So just as a small example, let's go back to treewidth, because we love treewidth. So if G has treewidth that means W, then the neighborhood complexity of GK is at most this function, so linear in K. So I think I can show that. It's too difficult. But essentially what you will see is that all these sparse graph classes are linear neighborhood complexity, so that means there will be some function of the class, and then there will be a your K. Okay. So as compared to, in general graphs, 2 to the K, and this is completely reachable. Like imagine just any graph where your X is of size K and you take all the possible neighborhoods, right? I mean, it's easy to construct such a graph. It could even be bipartite, actually. So creating, but of course, as I said, this is far from being sparse.
There's some relation to BC dimension also?
There will be, yes. I will define BC dimension after the break. There will be a relation. Exactly. So actually, I don't know if this theorem is known anywhere. Well, this was found by me and my friend Aline Parot. We were thinking about these things, but it's more like wondering about these things. But generally, I mean, since we know it's linear for much larger classes of graphs, these precise functions, I don't know if it has been studied precisely somewhere. Maybe it has. So how do we do? We take our 3D composition of width of a view, we move it here. This is my 3T. And okay, we have our set X, right? X, let's say this is X1 to Xk. I take any X, set X of this for this precise set, the neighborhood complexity would be at most this. How do I do? Okay, you remember for when you look at this tree, every vertex corresponds to a subtree. Right? That's the subtree where of all the bags, of the nodes whose bags contain. So let's call this T1 or X1. And then we'll have T2, etc. And so on and so forth. Okay. So what I'm doing, so I have k subtrees. I'm doing only for these vertices of my X. And I want to count how the other vertices can intersect these k vertices. So what I will do, I will prune my trees. What I do, I start from the root and I go down. Oh, by the way, I will, each of these subtrees has a root, which is basically the closest node to the root of that subtree. Sorry?
What is T?
T is the T from my tree decomposition.
And what is this?
Huh?
Okay.
So I'm taking a tree decomposition T, and with the set of bags. Right? So this is a tree decomposition of width W. It takes the vertex set X. This is the vertex set X, which corresponds to my neighborhood complexity. X has size K. I want to show that for any such set, right, the number of neighborhoods will be at most this inside my set.
So X1, X2 have vertices?
X1, X2, Xk are my vertices. So what I have X, X1, X2, this is in G. X3, up to Xk. Okay? These are my vertices of my X. When I look at them in the tree decomposition, you remember that when I look at the bags containing a precise vertex, it forms a connected subtree. So these colored things are the connected subtrees.
Corresponding to those vertices.
Yes, so T2 corresponds to X2. That's basically all the bags where X2 is inside. T1 is all the bags where T1, X1 is present. Thanks for the remarks. So it's also a nice way to go back to treewidth. Okay, let's do one more. T3, if it's root. Now I want to prune. Okay, so by the way, there will be parts of the tree which are completely white. That means they are completely untouched by any vertex of X. I mean, these parts I really don't care. Because I will only care of those vertices who will be inside the same bag as one of these colored vertices. Right? Because these will be the neighbors of X. Right? I will care about, I mean, of course, these guys inside X, in fact, they will count for K vertices. But what I'm really interested in is who is the neighbor of these people in X. The ones which are here and which never touch X, I don't care. They will count for 1 maybe for the empty set. Maybe there will be a +1. It's not really important. What I really have to count is the number of vertices which are present in some bag with these things. But it's not just counting those vertices. I want to, of course, count the different neighborhoods within this. Okay, what I do, I prune the tree. So I start from the root. Let's make it slightly more generous. Root doesn't have to be colored. I take the root of T2, it's from R2. And as long as there is no other subtree touching it, I keep, but then I prune. So I do this. here because this is already in the purple tree. So I only keep the ones which are singly in the tree. Okay. So I do this top down, you know. Like that. And it should be like that.
Can you please repeat that?
Sorry? Yeah, to T tilde is, so I go from root to bottom. And as soon as I reach the root of one of my trees, my subtrees, I keep it and I go down, but whenever I reach another root, I stop. I cut this edge. So I cut the tree. So this tree is pruned, it is smaller. And it is only blue. I have not mixed the colors. Next one, now this is not only yellow, now I could have these blue parts, but I prune only when I reach another root.
So when you're pruning, you're not even taking the vertex in common.
No, I'm not taking the
So only maybe one vertex is there in the curve.
one edge is there. Okay. Like this, right? That's what you mean? So I cut at this edge. What will happen here? Same thing, I will cut here.
Can two such roots overlap?
Yeah, yes.
And then in that case, what?
Then I don't know what to do. Okay.
One of the connected parts.
You merge them and you keep the union. Something like that. Yes. Probably. I didn't think of this one case. All right. Now what I want to say is that for each of these, so I have k subtrees, k of these k t tilde. Okay. What are the vertices of x which can be seen by the vertices in the bags of this subtree? These vertices correspond either it's the purple vertex, or it's a vertex from a top tree. Like if you look at this tree, it has blue and purple. That means the subsets I can create within X, the neighborhoods I can create within X, will be just subsets of blue and purple. I will not see this. And each time, in fact, what you see is that this subtree, since I have pruned whatever comes below, this T tilde subtree only sees the vertices of X which are upper here in my tree. But these, this set of colored vertices, which is seen, let's say, in the green T tilde, this is T4 tilde, all of them, they meet in this root. So that means there's at most W of them, W plus 1. Because all of them are in this bag. Okay. So for each T tilde, the vertices which are in this T tilde, they will see only W plus 1 vertices. So they will, their intersection with X will actually be an intersection with this, with one bag of the tree. And how many options there are? 2 to the W. So for each subtree, so I guess the constants are not exactly precise here. You get at most 2 to the W plus 1 and possible neighborhoods. Within X. But how many subtrees there are? K. So it's K times 2 to the power W. Where does the W come from?
So this for one bag or
Sorry?
this many subjects for one bag?
2 to the W plus 1 will be for one of the subtrees. But I defined k of these subtrees. Right? So it's k times this. Is it clear that for each subtree, prune the subtree, you will see only a subset of vertices which they are all present in this root band. So in particular, there is at most w plus 1 of them. Okay. So the number of possible neighborhoods, since it's a subset of w plus 1 vertices, is 2 to the power w plus 1. And this is times k because I have k subtrees. And where does this w come from? Well, you certainly have a plus 1 because of the empty set. Maybe there is some argument missing. Unfortunately, my notes stopped there, so I didn't have the end of the argument.
Maybe the root which we are deleting, we are cutting off from where we can have that W.
Start.
So by the way, what happens for trees, I think there is a nice, maybe different argument, but maybe the same argument, that will be in the problem sheet for trees, and this is,
This is, you published it somewhere? The theorem you showed us last?
no, this is not published.
Okay.
I mean, actually we started working on this thing, and then we saw that, oh, I mean, this has been done for all these classes with bounded expansion, so we said, okay, there's no point. I mean, maybe one could still optimize, you know, the numbers that we haven't done. Maybe we could do it. So Slater, so Pete Slater, he was quite an influential graph theorist from the US. He invented many concepts. So he was working, it was not called this neighborhood complexity, but on this location domination set, which I didn't define yet. But in this context, he proved that if G is a tree, if T is a tree, so this is published, however, there's a nice small proof, it's like one paragraph proof. Then the neighborhood complexity of Tk is at most like 3k. And this is set. Which, by the way, corresponds to 2 triple W plus W. So this will be in the tutorial, so you can think about it. Maybe adapt this proof. The proof of Slater is a bit different. Okay, with this colleague Douglas Roll. They also have a bound for planar graphs. So for planar graphs, it's 7. Okay, so if you're interested, they also have bounds for autoplanar and so on and so on.
Are they right?
Sorry?
This is right?
I think this is right. So typically, if you take geometric intersection graphs, you will get polynomial things. So this is not difficult to observe, but we had it in one paper, 2017, that if J is an integral graph, then you have essentially k squared. K squared. What is an interval graph is you take segments like that, which are all like parallel, and you put the vertex for every segment, and you make them adjacent if they intersect.
Is that big O?
Yeah, it's a big O. It's something like, you know, k plus 1 choose 2. The O is not big. Something like that. This is not difficult to observe because what you can see is that if basically if you take the intervals which corresponds to x, how do you intersect your x? Well, you start somewhere and you end somewhere. So this gives you, you know, roughly k starting points, k end points. It's like k squared. Well, it's kind of easy. But such a bond is also for other graph analysis. So anyway, you can study these things. And this is, as I said, related to the concept of locating the unity set. I will mention this because I like this concept. This was my PhD topic, locating dominating sets. What's a locating dominating set? Well, dominating is not that important. Locating, right? So it's a set X. It's the, let's say it's a set X of the graph, such that neighborhood complexity of, let's write it like this. Gx is essentially all the matrices. It's not exactly the original definition, but I want to write it in this language. Basically, essentially corresponds to this. So what you are doing there, you're trying to find a set X so that everybody has a different intersection inside the set. So you have your set X, and now everybody, okay, it may not be a dominating set because there could be a unique one which is not dominated, as you see, but everybody else should see a different name within that set. But now the challenge is to minimize X, and to find the smallest X. So the rotation, the LD number, that is the smallest size. Of rotating set. So in fact, I mean, these all the results I presented so far, they were not proof for the neighborhood complexity, they were proof for this, but it's really easy to translate. So essentially they were saying that your locating dominating set will be at least something if you have any graph, blah blah blah. But this really translates.
Does it always exist?
I mean, in this definition, not really, because if you have open twins vertices, it will not work. So that's why it's not really the initial definition. The initial definition is that you are not looking at the vertices inside X, you don't care. You only look at the outside. So if you put everything in X, it works. Or you could say, I just look at twin-free graphs. It's not the exact definition, but I just want to give you a flavor. But this is also, so this is a very rich area. There are lots of papers. I did my PhD in that. My PhD student did his PhD in that, and so on. Lots of nice things. Some of you are working on this, I know.
There will be exactly one vertex not adjacent to the set, right?
At most one.
At
At most one. I mean, they could all be dominating. So if you insist on the dominating part, you don't allow that single vertex. If you just want to say locating set, then you allow that one single vertex. So different notions have been studied. This in fact has been studied also. You know, this was invented by Pete Snyder in the 1980s, but previous notions, equivalent notions, have been studied for hypergraphs by classic people like Remy and others. I just want to relate this a little bit to that, part of the literature. Okay. And this is also related to the VC dimension. So I think it was mentioned 1 or 2 times. And I think it's a nice concept to know about, so I will just take this opportunity to introduce you to this concept. It's a little bit related to it. It will not be the main focus. By the way, the VC dimension, if you have looked at this graphic, it appears, it is here on the very top. So it is, so VC dimension is a graph parameter, which is mostly, I mean, primarily defined in hypergraphs. But you can define it on a graph by looking at the hypergraph of the neighborhoods. And it will look a bit like this. It will be similar to the neighborhood complexity. And when you look at graphs, this is a very, how to say, like graph classes of bounded VC dimension contain all of these things. All of these classes we have to be specific, almost all. They have all bounded VC dimension. So it's kind of, how to say. Still, if you bound the VC dimension, you're not very restricted, right? So it's kind of a general parameter in that sense. But still, you can say interesting things. In particular, for graphs of bounded VC dimension, this neighborhood complexity will be polynomial, it will not be exponential. So for bounded expansion, we will see later that it is linear, but for bounded VC dimension, it will be polynomial instead of exponential. So I think it's good to know this VC dimension. So VC doesn't stand for vertex cover, it stands for Vapnik and Chavonik. VC, this is Vapnik. Chavonikis, I suppose these are probably from technicolor, but I'm not sure.
Why not CV? No, we expect CV, right?
Yeah, not all the communities in science, use alphabetic order. Maybe this was the supervisor and was the student. say it is VE. So what is this? This is a set of vertices. This is a set of hyperedges. Hyperedges are what? They are just subsets of vertices. Okay. So a graph is a hypergraph where every hyperedge is size 2. But now hyperedges may have size 0, it could be empty. May have size 1, may have size 2, 3, 4, 5, anything. If you want to represent it with a picture, we had a nice picture, I think, yesterday by Rainer. These are your hyperedges. They could be, so this is a normal edge, like in graph sense. Like this. This is a hyperedge, it's empty. And so on. So this is your hypergraph. This is E1. So the computer scientists like to call this set system. It's just the same. Mathematicians call it hypergraphs. So this doesn't give us the definition. So before this, I will say that a set S of your vertices of H is shattered if for every x, or let's say S prime, in S, there exists a hyperedge such that E exactly intersects my set in S prime. Let's make a picture. I have my set S. Let's say it has size 3. So shattered means like it's cut into all different pieces, possible pieces. It means that I will find so this is not a hyperedge, by the way. Okay. S. I will find a hyperedge. So there are of course other vertices in my hypergraph. I will have one hyperedge which doesn't see anything in S. I will have one hyperedge which sees everything in S. I will have one hyperedge which sees only one here. Okay, now I need all the pairs. Triple I have. The pairs. And here you get it. Okay? So for every subset of my S, I need some hyperedge which intersects this subset exactly. Which intersects S exactly in this subset. Okay. If you think of the neighborhood complexity, you see how this is related in a sense, because if this was if these were neighborhoods of your vertices, it would be like having neighborhood complexity 2 to the power. If this was x, 2 to the power size of x. That's what I said earlier. When you looked at this neighborhood complexity, the maximum you could get was 2 to the power x. So the set is shattered. Well, now it's a hypergraph. It's not neighborhood, but we will define it in graphs, and it will be exactly that. If all the possible neighborhoods are possible here. And what's the VC dimension? It's the size of the largest shattered set. You can always find a shattered set of size 0 or 1. So the challenge is how large can it be. So the VC dimension of H is the size of a largest shattered set. Why is this interesting? So, the motivation of Vatnik and Chaboninkis, so these were actually people who were doing machine learning. So if you talk to people who, So I think essentially I know at least two communities who usually know about VC dimensions, the people who are doing what do you call it, geometric algorithms, algorithmic geometry, especially covering and packing points. I mean, you have objects in the plane or something like that. You want to cover or pack them. Because inherently these geometric objects have small VC dimension. So you have a lot of results around that. And the people doing machine learning. Because it was proved, I think by Valiant, that if you look at your data, right, I mean these learning algorithms, they process the data. The data is essentially you can see as a hypergraph. And if your data has bounded VC dimension, then there is one form of learning which is called pack learning, probably approximate counting, which performs very well. So if your VC dimension is small, this algorithm is kind of optimal. If your VC dimension is not small, this algorithm is not good. So it's kind of a dichotomy theorem, and so that's why people do machine learning, they usually know about it. At least the ones who are doing a bit more of the theory of machine learning. So this was the motivation. This was, maybe 1970s or something. Now you can say that when you do graph classes of boundary expansion, you're doing machine learning. This is good. You get grants. Because all of these graphs have boundary VC dimensions. Alright. Okay, and how do we define this for a graph? These definitions, I will not really use them. I just want to show you these concepts because I think they're important and I think it's a nice place to mention them and then you know about this and use it someday. For a graph, so VC dimension of a graph is essentially the VC dimension of the hypergraph you get by taking the neighborhoods. I mean, actually there are many possible ways. You could take any subsets. You could take paths, you could take connected sets, etc. There are some papers which study this, but the most used are either the closed neighborhoods or the open neighborhoods. There is also a version where you look at all the balls of all the possible distances. This is called distance VC dimension. But yeah, anyway. Dimension of the graph is the VC dimension of its open, closed, depending on the case, neighborhood hypergraph. Hypergraph, so this is H, which is equal to D of G, and the hyperedges are just D. If I take the open ones. Okay, so it's just the open neighborhoods. All the possible open neighborhoods. So this is a very special hypergraph. Actually, it's a linear hypergraph in the sense that the number of hyperedges and vertices is actually the same. It's a simple kind of hypergraph. If you take the VC dimension of this, and this is your VC dimension of your graph. So in this dimension there is a fundamental lemma, which is not so difficult to prove. The proof is actually on Wikipedia, on paragraph. says that if your VC dimension is small of your hypergraph is, let's say, at most d, then essentially your neighborhood complexity will be small. I mean, I didn't define neighborhood complexity for hypergraph, but I will say it like that. Then H is distinct average. Oh, what did I say? So this is true for every x. Ah, yeah, okay. It is true for any. Yeah. Well, okay, I will state it like that. With stronger form, I have to state it also. Nearly true. Yeah, distinct. So it says that the number of distinct hyperedges is a polynomial. So you can imagine that in some sense you want to, you have your set of vertices, V, and you want to look at how these hyperedges intersect your set. And there is only a polynomial number of possibilities instead of exponential. Instead of being, it could have been, in general, it could have been 2 to the power number of vertices. But if your VC dimension is small, so essentially what you can, this is a bit like, you know, the maximal number of intersections you can get in a small set. If that is small, then this lemma shows that, well, the number of hyperedges cannot be exponential. So, for graphs, the VC dimension of a graph is at most d. It implies that the neighborhood complexity of GK is then O of K to D plus 1. Let's call that. Why is this? Because you take your set X, you are going to look at the hypergraph, which you get by looking at the neighborhoods within X. This gives you a hypergraph, right? Everything which doesn't intersect X, you don't care. Take this hypergraph, but you know the VC dimension of your G is at most D. So this is also the VC dimension of this. This is exactly the VC dimension of this hypergraph. If you remove things, you cannot increase the VC dimension. So I've just cleaned it up in some sense. VC dimension stays small. So the number of possible intersections I get is just the number of hyperedges, distinct hyperedges of this graph, of this new hypergraph, and it is by this lemma. It is polynomial in the size of number of edges, which is k. K being the size of my set X. And this kind of explains, you know, these results I was telling you about planar graphs, interval graphs, and so on, because they have small VC dimensions. If you think, you can think about it, planar graphs. 3 or 4.
Less
5?
than 5. Less than 5.
Less than 5. At most. You mean at most 5 or at most 4? At most 4, I guess, no?
Correct.
Yeah, I think planar graphs have DC dimension at most 4. Interval graphs have 2. If you take these unique disk graphs, they have also small DC dimension. Maybe 3 or 4. So all these kinds of graphs are quite nice. They have a small neighborhood. Okay, what about the graphs of bounded expansion? This will immediately give us a bound, actually, but it will not be linear. What's this? Corollary by observation. If C is a class of bounded expansion, then every G C has DC dimension at most. What did I write? For f of 0. Where f of 0 is the expansion function. Let's see what I mean by that. So you have your graph class of bounded expansion. And suppose you have a shattered set X. So now we are looking at the neighborhoods, open neighborhoods. These are vertices. So that means there is somebody who intersects here, here, so all the pairs, all the triples, etc. So it creates something quite dense. So I will now. Any questions? F of 0. So this is look at the subgraphs. F of 0. F of 0 is a fundamental here. But if you look at this and X is large, well, what you will find a very large declic. Declic is what? Is a complete bipartite graph. Right? Because if you let's suppose it is even for the sake of simplicity. Xk, let's say y1 to yk. And since this is shattered in particular, what you will find all the sets which look like this, that they contain exactly this neighborhood plus one from the top. Etc. Because these are all distinct subsets which are completely valid. So now in my graph I have this huge complete bipartite graph. So this will give me a complete graph on 2k vertices, kk, right? Because all of these vertices, I mean they will have distinct neighborhood with an x, but they will all share all these neighbors, which is k. There will be k of them because each of them will be connected to one of these. So what I'm saying is if you have BC dimension at least k, you will find a large declic. But if your graph class had unbounded BC dimension, so there would be a graph of, for every BC dimension, value of BC dimension, you would find a graph which has this BC dimension. You would find these kind of subgraphs. But these are very dense. So you would find arbitrarily large, dense subgraphs. And this is not possible. Because this graph has basically, what's the density of this graph? So you have 2k vertices, and there are k-squared edges. So the edge density of this subgraph, of this kk. So edge is, what did I say, k squared? And there are 2k. This is equal to k by 2. And we know that this should be at most f of 0, so it's 2. No, because the VC dimension was 2k. So I get that VC dimension is 2k. Which is at most 4 times fx. Yes, because k is at most twice fx. So the VC dimension of my graphs is at most this, so it's constant actually. So if you have a graph class of bounded expansion, you have some constant VC dimension, where this constant depends on this huge function f. You don't have control on that. Any question?
So did you get VC dimension to k?
So I took a shattered set. I assumed, I mean, for simplicity, I suppose it's even. I take the largest even shattered set. Maybe VC dimension is 2k plus 1, but I take 2k. If I have this, I find a large bicyclic, a large bipartite graph as a subgraph, k, k, k. Okay? But this is a subgraph. So it's a depth 0 shallow minor. It's a depth 0 minor. So by the properties of bounded expansion, class of bounded expansion, I know that this edge density is small.
So the given graph was KKK or not given the...
No. You have a graph G of your class C. I assume, I look at the VC dimension of it. So I suppose you have a set of even shattered set, 2k. I find a large bicyclic. Okay, KKK.
So KKK is pre-invent, right? You create new edges and...
No, it's a subgraph, because if this is shattered, this being shattered means that for every subset of this, I have a vertex whose neighborhood, intersection of neighborhood with this x, is exactly this subset. So in particular, there is this vertex which sees all the y's and x1. There's another one which sees all the y's and x2. All the y's and x3, etc. But if you look at this part, if you look at all these vertices, you get a KKK. So this must be a subgraph of your graph. But I can prove you that there cannot be big subgraphs. Why? Because the edge density of a complete bipartite graph is huge. There are k squared edges. Number of edges is 2k, so edge density is k by 2. But I know that edge density is at most f of 0, because it's a depth 0 minor. It's a shallow minor, super shallow minor, 0. Okay, so k by 2 I know is at most f of 0. So that means k is at most 2f of 0. But I assume that the VC dimension was 2k. VC dimension being 2k. 2k is 4 times f of 0. This is an upper bound. So I know that the VC dimension is at most 4 times f of 0. So it is constant. Some huge constant which depends on that graph class. But this shows that graphs of bounded expansion actually they have small bicyclics. So the bicyclic number is the size of the largest complete bipartite graph with both sides of the same size. There's a small bicyclic number. And this implies a small VC dimension. Because in VC dimension you need large bicyclics. Anyway, this is not...
So we are rising this way, like this is upper one a subset of superset of the lower one.
Yeah, this diagram means that the upper classes are larger. These are the small classes. You see, you have 3, 4 edges, orthogonal graphs, max degree. The upper you go, the more general you are. So this graph of bounded peak number contains almost everything. Bounded VC dimension contains everything. Okay. So what I'm saying is bounded expansion implies small basic dimension. So it immediately implies some bound on the neighborhood complexity by this lemma.
But from the figure we can see anything with bounded expansion is also no variance.
Yes,
But the converse is not necessary.
correct. Okay, so the corollary of this C is exactly then every at least dimension is not f of 0 for f of 0 corollary by this our Scheller lemma that the neighborhood complexity of G k belongs to or k to the 4f of 0. So it's a polynomial. This is a constant. But what I just wanted to mention this. Trivially true, but something much stronger. I mean, I already announced it in the beginning of the lecture, but actually, this we can actually decrease to 1. The neighborhood complexity will be linear. Let me just another 15 minutes. I need more definition, unfortunately. Hope you'll forgive me. Sorry? Yeah. If G belongs to this class of bounded expansion, the same class, and the neighborhood complexity is polynomial. So I need a couple of more definitions. They are a bit more general than this neighborhood complexity, but you will. So the idea is tomorrow morning in the tutorial you will manipulate these definitions. Hopefully, they'll become clear. And what we'll see is bounded expansion is characterized by these things being bounded. These things which I have noted. So the first definition will be to generalize to any z. I think I announced it. So any neighborhood, any distance d. I will define the d profile complexity. Sorry, d neighborhood complexity. This is exactly the same, but with neighborhoods at distance d. Neighborhood complexity. Maybe I can take a little shortcut and say that immediately, directly, since you have seen the definition, this will be the maximum of over x in d of g choose k of the possible neighborhoods within x. Exactly same as neighborhood complexity, but I take distance d neighborhoods. Let's make a small picture. X. This is the neighborhood at distance d of v. This is simply all of the w such that all the vertices w with distance at most d from v. Okay, and you look at the possible intersections with x. This is the neighborhood complexity. And you look at, of course, for a given k, you look at the maximum distance. So you see that what I defined was basically the one neighborhood complexity. This is the d profile complexity. So what's the profile of a vertex for a given D? So it's the D distance profile with respect to a graph, some set X. X is a subset of vertices, and V is another vertex of G. Whose picture is like this: X, you have your V. But now what I want to do, I actually want to. So these are the vertices which are a distance at most D. But instead of here, and just basically here, this is kind of a binary function. Either you are in the neighborhood or you're not. Either you are distance at most D or you're not. Now I want to refine this by actually keeping the values of the distances. So let's give a precise example. I will take D equals 3. What's the profile of this vertex? It is basically the vector of distances. 2, 2, 1, 3, and this is too much, so I put it in. So this is the distance profile of D with respect to my set X. So X may have many other things. Well, actually no, X has just 4 things. It has 4 vertices. I look at all the ones which are distance at most D. Then I put the exact distance of it. 2, 2, 1, 3. For the ones which are too much, I put infinity. I kind of cut. So if I want to be a bit formal, I say that the profile is a function and for every x in my x, so it's a function which is associated to V. But that function gives to every vertex of x one value. It receives the distance from B to x if it is at most D and infinity other x. This is just a formal way of saying what I just showed on the picture, that this is kind of a ordered set of distances. But I don't say it like this because that would imply that you need to define an ordering. So that's why I write it as a function. It is more formal. To every vertex you associate one value. This is the profile of a vertex D with respect to x. The D profile, distance D profile. It's a kind of a refinement of this. Here, as I said, it was zeros and ones. Here I actually have the actual values of the distances. Or infinity if it's too much. Okay. And now I can define the profile complexity. So the profile complexity of a graph G for a given size of sets is the maximum over all x's of that size. Okay. Of what? Of the number of distance profiles. Of D. D is in count, instead of counting the number of different neighborhoods in neighborhood complexity, you count the number of profiles. Okay. And this is, of course, this is a refinement when we have neighborhood complexity.
So V is fixed. The vertex V?
V is fixed. No, V, we go over all vertices.
Okay.
So you look at all the vertices of the graph.
So the maximum is over X and V.
Max is over the subsets X. For every subset X, you fix X.
Yeah.
Now you look at all the possible profiles for all the possible vertices. You look at V.
Oh, I see. Okay, sorry. Yeah.
The profile corresponds to one given vertex. You look at all the different ones.
Okay.
And you see how many there are. It's really like before. Like before, we were looking at the neighborhoods, all the possible neighborhoods. Now we're just refining, and we are just taking the profiles instead of neighborhoods. And yeah,
Profile is a vector, right?
sorry? Profile, if you want, it's a vector or it's a function. I wrote it as a function. It's a function or a vector. But it's ordered in the sense that you want to associate to a given vertex its distance. Right? So what I mean is like 1, 2 is not the same as 2, 1. Right? I mean, this will be for x1, x2. So better to see it as a function. But maybe it's a bit too formal.
Is V isn't a V or isn't V minus X? Or like do we
V
consider
is in
X?
V.
V is in
Yeah, but it's like before, like the guys in X, they anyway count only for X different, not X different profiles, and actually they are the only ones to be at distance 0 themselves. So they don't matter too much. But one observation is that the neighborhood complexity is at most the profile complexity.
If it's infinity, will profile complexity become infinity?
Sorry?
Will there be infinity if we get an infinity there? So 2, 2, 1.
Here you don't have infinity. Here you don't have infinity because you just look at the ones which are basically not infinite. So the ones which are here in this definition, the ones which are at most d distance, they are in your neighborhood. The ones which are not, they are not. Here, the ones which are inside, they actually get precise values. And the ones which are not, they get infinite.
So when you look at the modulus, how do you take that?
Yeah.
Like when you look at the cardinality of the set,
So this counts the number of different profiles, each profile being a function. So you look at how many functions you create with x inside your graph. Okay? We will give an example. Let's give an example with x being this. Let's say d equals 2, so this guy receives infinity. This guy receives 2, 3. This guy is 1, 2. This is 1 infinity. This is more than 2. This is infinity 2. This is 0 infinity, and this is infinity 0. Okay. Well, in this case, I have let's put 2 here. These two are the same function. How many functions I have? 1, 2, 3, 4, 5, 6, 7. Profile complexity 2 of gx equals 7. 7 different profiles. If I was to count the neighborhoods, you can see that I would have much less. Actually, let's do it. If I look at a particular set X, what's the possible neighborhoods? So, 3 is infinity. So this sees nobody, it points for 1. There are a bunch of them who only see the first one, a bunch of them who only see the second one, and those who see both. In fact, you can have at most 2 to the power 2. Right? So in this case, you actually have 4. The neighborhoods will be, empty, x1, x2, or x1, x2. At most 4, and in this case, it's really 4. really see that the neighborhood complexity is small. Okay. Maybe one. Time to wrap up, but one last definition, which is another thing I like, so I want to squeeze it in again. It is called the metric dimension of the graph. It is the
So there was also 2, 1.
sorry. Size of the smallest set x with the profile complexity n.
There's 2, 1. So there's a small question over there. For
Yes.
x2's neighbor, there is one that should be 2, 1.
Which one? Ah, this one?
Yeah.
Yes, this is the one here. So you see from the perspective of distance to neighborhood, these two are the same. Because they both, at distance 2, they both see x1 and 2.
So they are saying 1, 2, and 2 are the same? Or
For neighborhood complexity, they're the same. For profile complexity, they're different because this is 2, 1, this is 1. Okay? So profile complexity, you really look at the precise distances. So 1, 2 is different from 2, 1. But for neighborhood complexity, it's either you're in or you're out. So in this case, they're both in. So this is both x1, x2 at distance at 2. This is both x1, x2 at distance at 2. So they have the same neighborhood within the distance 2 of x. Within x. Alright? Okay. One last definition. But this is a fun one, I really like it. So this is also the Slater from the 70s. This is an old concept which is quite popular. Slater 75 and also Harari and Melzer 76. So they did it kind of independently. I don't know if there was communication or not, but at least these are two different papers. This is quite a popular concept in graphs. What you are looking here, you want now the smallest size subset, such that everybody has a different program. But you don't restrict the distances, so that's why I put n. So n will be the largest. So you can reach everybody. Let's say you have a connected graph. So that means everybody has a different distance profile to your set, to your solution. And now you can be arbitrarily long, arbitrarily far. This is my set S. This will be 0, 2, 3. So you can think of it like giving coordinates. Here it will only increase. So these are the three distance values you can think of as coordinates with respect to this set. In fact, this is kind of, you can imagine what happens when you have a GPS. When you do GPS, what happens is we have the planet Earth, and we have these satellites, right? This guy. And how does it work, GPS? Well, when you're somewhere, so these guys send a signal, and because they send the timestamp, you know the timestamp, you know the velocity of light, so you know the distance to your satellite. So every point of the Earth knows the distance to a bunch of satellites. Not all of them, because some of them are on the backside. That's how your GPS works on your phone. So you receive these signals and you know the distances to these different satellites. And by that you can triangulate your position, and that's how you know where you are. So in some sense, everybody on the surface, at any given point of time, has a different distance profile to the satellites. So this is a graph version of it, right? Of GPS. This is called metric dimension of G, and it's quite a fun thing, whether on the structural side or on the algorithmic side. There's been quite a lot of work in the last, well, since this time, but also in the last decade or so. This is quite nice. I just wanted to mention it as a possible research problem for you. If you like this, you can look at the literature, or you can ask me. I can point you to some references. Okay, last thing I want to say. This will not be a definition, it will be a new characterization of boundary expansion, and this is kind of why I wanted to tell you all these things. And tomorrow we will have a tutorial about these things, and after that I will give you, as before, a proof of one side of the result. And so this is another big theorem. So this is by 2017 by Euler, Sanchez-Villamil, and Stavropoulos, 2017. Okay. Again, this is one of the papers which is quite readable. It's not, proofs are not that long. So the theorem is, let's see, the class bounded expansion. Let's see the class of graphs. The following are improvement. Again, we will have three things. C has bounded expansion. There exists some function f1 such that the neighborhood complexity of graphs in C gk, well, for every g, for every k, for every d. So that there exists a function f1, which, so they have a linear neighborhood complexity, but this linear term depends on d, which distance you're looking at. But the important thing is that it is linear in k. Remember that in the worst case we could have exponential in k. When the VC dimension is bounded, it could be polynomial in k, but still not linear. And the third one is that the profile complexity is also bounded. There is a function f2. So this is really nice characterization. So it's really like if and only if. Probably we need monotone. Maybe we need monotone here, by closed on the surface. I'm not completely sure. Let's put it just to be safe. Okay. So we know that, well, 3 implies 2 because if you have bounded profile complexity, you will have bounded neighborhood complexity. What I hope to show you next time No, I will show you. I will show you the one in place 2. Sorry, one in place 3. One in place 3 I can show you. 3 in place 2 is easy, trivial. Actually, it's the observation which was in here. Okay. 1 in place 2 tomorrow. And as you know, 1 in place 3. What is missing? 1 goes to 3, 3 goes to 2, 2 goes to 1. Is left as an exercise. Of course, that's the most difficult one, so this is a joke, it's not an exercise. But, I will not do it. But you know, it is not that long. If you look at the paper, it's like 1.5 pages. Might be a bit compressed, I don't know. I think it's not crazy. It's quite nice. And in fact, you know, in the paper, they actually give 2 proofs of 1 in place 3. And one of them uses these coloring numbers. So that's the one I will choose. So we are going to use the coloring numbers again. And it is another nice application of these coloring numbers. Bounded expansion. I put monotone. I'm not completely sure if it's required, but for safety sake. I think it's not required that much. Okay. So, yeah, we've seen a lot of things today. These weak coloring numbers, strong coloring numbers. We have seen how to characterize, at least one side we have seen bounded expansion using the coloring numbers, and now I've defined all these notions. I hope it will be okay. Neighborhood complexity, profile complexity, d-neighborhood complexity, etc. Metric dimension. But anyway, the main purpose was to show that this actually gives a characterization of classes of bounded expansion. And this has nice applications. You know, if you are, so it is applied, for example, in algorithm when you do kernelization. So you want to find kernels for some problems in parameterized complexity. Well, you can see why, because you know that if you get something which has too many same neighborhoods, I mean, I suppose you can reduce it and so on. I don't know too much about it. But that's all right. That's enough for today.